Welcome to our lecture on the diversity of chordates. Today, we are diving into the fascinating world of Reptilia. Think about a hot summer day when you see a lizard perfectly still on a sun-baked rock. Have you ever wondered why they do not just stay in the shade like we often do? By the end of this video, you will understand exactly why and how these incredible creatures became the first vertebrates to truly conquer dry land. To begin our journey, let us formally define what makes a reptile a reptile. In biological terms, the class Reptilia includes turtles, snakes, lizards, crocodilians, and the tuatara. They are defined as ectothermic, amniotic, air-breathing tetrapods. But what does that actually mean? Ectothermic means their internal body temperature is regulated by external environmental sources, like the sun, rather than an internal metabolic furnace. Unlike amphibians, which have moist skin and are tied to water, reptiles evolved thick, dry skin covered in tough, keratinized scales. This waterproof barrier prevents water loss, meaning they must rely entirely on their well-developed lungs to breathe. Now that we understand their basic physical traits, let us look at their most significant evolutionary breakthrough. Reptiles represent the critical evolutionary bridge between water-dwelling ancestors and all fully terrestrial vertebrates, including birds and mammals. Before reptiles, animals like frogs and salamanders were forever tied to the water because their jelly-like eggs would dry out and die on land. Reptiles solved this massive problem by evolving a magical, self-contained life support system called the amniotic egg. This single innovation meant that life was no longer tethered to the edges of ponds and oceans. This evolutionary breakthrough we just discussed is perfectly illustrated here. What you are looking at is the cross-section of an amniotic egg. Notice the developing embryo in the center? It is surrounded by multiple specialized membranes. The amnion protects the embryo and retains moisture. The yolk sac provides vital nutrients. The allantois stores waste, and the chorion facilitates gas exchange. Look at the arrows on the left and right. Oxygen enters through the leathery shell, and carbon dioxide exits. This incredible self-contained capsule provides everything the embryo needs, allowing reptiles to lay their eggs in completely dry environments. Having seen how they reproduce on land, let us shift our focus to how they survive day to day. To truly understand how different a reptile is from a mammal, we have to look at their energy usage. Because reptiles are ectothermic, or cold-blooded, they do not waste precious energy generating their own body heat from the inside. Instead, they use the environment. This results in incredible energy efficiency. Studying this reptilian physiology helps scientists understand how these animals can thrive in extreme environments, like scorching deserts where food and water are incredibly scarce. This biological reality of energy efficiency can be expressed mathematically. The formula you see here is the allometric scaling equation for metabolic rate. It tells us how much food and energy an animal needs just to stay alive, based on its size. P represents the basal metabolic rate, which is the total energy used per day in kilocalories. M is the body mass in kilograms. The symbol A is a specific constant that depends on the animal group, and it is much lower for reptiles than mammals. Finally, B is the scaling exponent, usually around 0.75. If the constant A decreases, the total energy requirement P drops dramatically. Before we move on, Let us see this formula in action with a concrete example. Imagine we have a small dog weighing exactly 3 kilograms. We want to calculate its basal metabolic rate. We are given the mass, m, equals 3, and the scaling factor, b, equals 0.75. For mammals, the metabolic constant A is approximately 70. We plug these values into our allometric scaling equation. First, we calculate 3 to the power of 0.75, which is approximately 2.28. Multiplying 70 by 2.28 gives us a final metabolic rate of 159.6 kilograms per day. This is the energy the dog needs just to survive. Now that we have calculated the mammal's energy, let us do the exact same calculation for a reptile of the exact same size. We have a lizard that also weighs 3 kilograms. The mass and scaling factor remain identical. However, for reptiles, the metabolic constant A is roughly 10, much lower than the mammal's 70. We substitute 10 for A and 3 for M into our equation. The scaled mass is still 2.28. Multiplying 10 by 2.28 gives us a final answer of 22.8 kilocalories per day. Physically, this means the reptile requires about 7 times less energy to survive than the mammal. This explains why a snake can survive on just 1 meal a month. This incredible energy efficiency brings us to another important physical reality for reptiles. Because they do not generate their own heat, they rely entirely on the sun to warm their bodies. The physics of this warming process is fascinating. The rate at which an object absorbs heat from the environment is directly proportional to its surface area. However, the amount of tissue that actually needs to be heated is proportional to its volume. Therefore, how quickly a reptile warms up in the morning sun is entirely governed by its surface area to volume ratio. Let us look at the mathematics behind this. To understand this heating process mathematically, we use the surface area to volume ratio formula. For simplicity, we can model a reptile as a cube with a side length of S. The ratio R is simply the surface area divided by the volume. The surface area, SA, of a cube is 6 times the side length squared. This represents the skin exposed to the sun. The volume, V, is the side length cubed, representing the internal body mass that needs warming. As the side length S increases, the volume grows much faster than the surface area, which means the overall ratio R will decrease for larger animals. Let us apply this formula to see why small lizards heat up faster in the sun. Consider a baby lizard modeled as a cube with a side length S equal to 1 centimeter. We want to find its surface area to volume ratio. First, we calculate the surface area by plugging 1 into our formula. 6 times 1 squared gives us 6 square centimeters. Next, we calculate the volume. 1 cubed is simply 1 cubic centimeter. Finally, we divide the surface area by the volume. 6 divided by 1 gives us a final ratio of 6. This is a relatively high ratio, meaning there is a lot of skin area to absorb heat for a very small internal volume. Now, let us compare that baby lizard to a fully grown adult. We model the adult lizard as a cube with a side length S equal to 5 centimeters. We calculate the surface area. 6 times 5 squared gives us 150 square centimeters. Then we calculate the volume. 5 cubed is 125 cubic centimeters. Dividing the surface area by the volume, 150 divided by 125 gives us a final ratio of 1.2. Notice how much smaller this ratio is compared to the baby lizard's ratio of 6. This physically explains why small reptiles can dart around quickly early in the morning, while massive crocodiles take hours of basking before they are warm enough to move. We have covered a lot of ground today, so let us summarize the key takeaways. The class Reptilia represents a monumental leap in vertebrate evolution. By developing tough, waterproof skin and the revolutionary amniotic egg, they completely severed their reproductive ties to water and conquered terrestrial habitats. Furthermore, their ectothermic metabolism grants them incredible energy efficiency, allowing them to survive on very little food, even though it requires them to carefully manage their body temperature using the sun. You now understand the biological and mathematical reasons why reptiles are some of the most resilient survivors in the animal kingdom. Great job!